In this video, I would like to discuss end of chapter question 4 from chapter 23 from the book Chemistry Cubed. And I will just briefly read out the question. A synthetic route to the naturally occurring terpene geraniol 13 is shown here. First question, suggest reagents that will convert 14 into 15. Okay, I've actually not shown the structure of the natural product here. It's the end of this whole synthesis route. We don't see that here, and actually none of the question is referring to it. And I would like to start now with the first question. So how can we transform 14 into 15? 14 is a carbonyl component, actually the C1 carbonyl component, so the most simplest carbonyl component. It's formaldehyde or methanol, and product 15 here, the carbonyl group is not visible anymore, and we are having a very extensive carbon-carbon or a carbon-based framework here in our product. And we are having here a primary alcohol, and we are having here a double bond. So now we need to think about how can we produce this starting from 14. And what we see in every case, we definitely need to form a new carbon-carbon bond between our molecule or starting material 14 and our reagent that we are using. And a nice way to now connect or to form new carbon-carbon bonds with a carbonyl component is actually the use of a Grignard reagent. And a Grignard reagent, if I can quickly sketch that here on screen, looks something like this. So it's a magnesium based molecule, and in general, you can have like a lot of organic rests here in this at this R, so on the left-hand side of this carbonyl or this Grignard reagent here. And in our case, we just need to find out what is the product here. What kind of organic rest do we need to attach to our Grignard reagent? Our Grignard reagent will overall attack here at our carbonyl carbon atom that is slightly positively charged, and we will in the end produce an alcohol from this. So this is probably the alcohol that is this primary alcohol on the right hand side of our target molecule. Let's highlight this. This is our former formaldehyde molecule, so all the rest here is needs to come from our Grignard reagent. In a way, I will highlight this in blue now, and in black we have the carbon-carbon bond that is newly formed during this Grignard reagent. So we can just take this part of the molecule here and add this to our Grignard reagent. In a way, I will just delete the group here, the rest group, and then connect these two things in a nice way so that it gets clear what we are talking about, and remove the color. So this is our starting Grignard reagent here in a way, and this can react. Of course, important to highlight here again is the use of dry solvents, because otherwise the Grignard reagent also nicely reacts with water, because it's very water sensitive, because we are having a negatively or partially negatively charged carbon atom here, and this also would like to react with protons that are readily accessible in water. And then after we have reacted with the Grignard reagent, we work up actually with water and acid to get this protonation step here. So this is the answer to the first question, and let me also add the protons to the reaction arrow to make this complete. So of course the protons in the second step. Okay, this is the answer to the first question. Next question is, give the structure of organic component 16. Why is it important to use dry ethanol, dry ethyl ether here in this case? And so structure 16 is the unknown structure here on the right hand side, top right corner in my sheet here. And actually we are having two reactions. First we are using this phosphor tribromide here, and after that we are using magnesium and the dry solvent to facilitate this reaction. Okay, what can we conclude? Or let's first analyze the question. We know the starting material and we know the reaction conditions, so we are actually looking for the product here in this case. And what we see is actually a two-step reaction sequence. So first we need to analyze what is happening when we react our component 15 here, so our primary alcohol with the double bond with phosphor tribromide. And what is happening here is the transformation of the primary alcohol into the bromine component in a way, because this phosphorus is very oxygen, has a high oxygen affinity, so it wants to react with the oxygen and in the end then push also basically a bromine onto the molecule here to say it a little bit non-scientific in a way, but I think the point is quite clear. So we are replacing our hydroxy group with a bromide group. And now we have our intermediary product here, and if we then use in the second step magnesium in dry diethyl ether, we can see that this is the classical formulation of a Grignard reagent, so magnesium metal plus halogen alkane produces the appropriate Grignard reagent. So we can just take that, copy our structure over here, and then basically insert a magnesium atom into the carbon or the former carbon bromine bond here. Let me quickly do that on screen. So we are seeing this, and then we are adding the bromine molecule here in the end. So this is our solution to the question, so structure 16 here in this case. Then to answer the question, why do we need to work with dry solvents? We have answered that in the first question already. The Grignard reagent wants to react with water. It has this partially negatively charged carbon atom here, and this can of course react with protons just as we've discussed. So it's important to really work with a dried solvent that we avoid any unwanted side reactions here in a way. Okay, third question is suggest reagents for two-step synthesis of ketone 17 from 16. So we are seeing here ketone 17, and our starting material is now this Grignard reagent that we have just synthesized, and we need to suggest two steps here, so one reaction arrow and a second reaction arrow, so there is an intermediary product here. So what do we need to do? Yes, we first analyze our starting material. We see it has a carbon framework that we've previously built up, and in our product we see that the carbon framework looks, we've already find our carbon framework here. So this is the fragment that we also have in our Grignard reagent. I just highlighted this here in red now. So these two fragments are actually the same, but what we don't have are the two carbon atoms here at the right hand side of our target molecule 17 here. And we are having a carbonyl group. So Grignard reagents can nicely be used to form carbon-carbon bonds, as we've seen in the initial step from the where we used formaldehyde. And what we now need to add to our Grignard reagent to form a new carbon-carbon bond is a carbonyl component. And because we want to add two new carbon atoms here, or elongate our chain and our carbon-carbon framework by two carbon atoms, we actually want to add a carbonyl component that has two carbon atoms present. So we can draw that. It would looks like something like this. So this is our starting component. It's actually called acetaldehyde, so the carbonyl component where we have two carbon atoms attached. And then our Grignard reagent, which is partially negatively charged, can attack here at our partially positively charged carbonyl atom in an electrophilic addition reaction. Nucleophilic addition reaction, of course. And then we end up with the product. So our intermediary product from the reaction of the Grignard reagent with our acetaldehyde is something that looks like this. Let me also remove the color, and we are ending up with an alcohol here in this case, because we are adding here and then we are protonating again. So we also need to add the protons in the second step. This looks something like this here. So we're getting the secondary alcohol here in this case, and for the second reaction step we only need to think about how can we selectively transform a secondary alcohol into a carbonyl group, and we can rather easily find that this is an oxidation reagent. We can, for example, use chromium tetroxide in water, and this then basically does the trick of transforming our secondary alcohol into the ketone component 17 that we are tasked to synthesize. And then next question, question 4, would be propose a mechanism for the reaction 17 with the shown bromine zinc component here. And then we are working up under acidic conditions to give the hydroxy ester 18. Yes, so the question also states that this reagent here is called the Reformatsky reagent, and the Reformatsky reagent is actually in a way exactly the same as the Grignard reagent, but instead of magnesium, which we used 2 times already in our reaction before, now we are using zinc. So it's slightly different, slightly other tolerances for other functional groups, but in the end the reaction mechanism is always is the same as the Grignard reagent, where the trick here is to produce this negatively or partially negatively charged carbon atom, which can then attack at our carbonyl atom that we have in our starting material. I will just draw the reaction arrow here in this case. This may be a little bit long. Maybe this one here fits a little bit better. So this is where the reaction or the attack happens, and then we are connecting that. We are, again, as we've seen 2 times now, we are transforming our carbonyl group into an alcohol. So this is the target molecule or the alcohol that's formed over here. We're having our methyl group that was previously this group here, and we are forming a new carbon-carbon bond, just as we've seen in the Grignard reagent. Reformatsky reagent exactly does the same thing. So this newly formed carbon-carbon bond here is highlighted in red now in this target molecule. So this is the reaction mechanism, exactly the same as in the Grignard reaction. And the last question, would you expect 14 or 17 to react more rapidly with the Reformatsky reagent? So we're having our structure 17 here, where we already have the what we already used, and 14 is, again, to recap, our formaldehyde molecule over here. Now we need to analyze which one of these reacts faster, and we can conclude, or what we can immediately see, is that 17 is actually a ketone component, and 14 is an aldehyde component, and it's even a special aldehyde. It's the formaldehyde. So the steric hindrance at molecule 17 here, at this ketone, is way larger. So the organic rest, on the one hand side, the methyl group, okay, that's not so bad, but on the other side we're having this rather long carbon chain. This obstructs a little bit the approach of the nucleophilic Reformatsky reagent here. And in the case of the methanol, we are not having the steric hindrance because the protons are actually the smallest substituents that we can have, so they are basically not really obstructing the approach of the Reformatsky reagent. So what we can conclude is that the formaldehyde would react way faster than our ketone component 17 here in this case.